Okay, let's start the next session. The next session is mainly focused on physical representation or physical reproduction. And the first talk is by Professor Iwai from Osaka University. And the title is Computational Projection Mapping for Optimal Material or Apparent Material Control. So please.
Thank you. And I'm very sorry because there is a sweets unexpectedly, because there should have a poster session this time, but we shifted, so that's why a little bit confusion. But yeah, let's start. So thank you. I'm happy to talk about our work on computational projection mapping for optical or appearance material control. So projection mapping is a well-known technology. I think I guess most of you know what it is. So basically, we project images onto physical surfaces, not only on a white screen like this, but general objects around us. So it is always widely applied in entertainment and advertisement. But at the moment, the impression of the projection mapping to me is more like changing the illumination pattern than manipulating the physical materials or reflectance properties. So to achieve the real material control, we need a new type of technology that overcomes technical limitations of the current projectors. So we apply the computational display approach, which is defined as the joint design of hardware and display optics with computational algorithms and perceptual considerations. And in addition to these components, I'd like to add one more. If we think about the whole projection mapping system, there is a missing but very important component. That is the surface. So we call this joint optimization framework as computational projection mapping, and developed several systems overcoming the current limitations by combining two or more components. And I'm going to introduce a part of our achievements during this Shitsukan project. The first limitation is defocus. So because projectors are basically designed to increase the brightness, the aperture is normally very large, which leads to a narrow depth of field, and then the projected image gets blurred even with a slight depth variation. So we extend the depth of field of a projector by focal sweep approach. In a normal projector, a projected pixel appears focused when the projection's surface locates at the focusing distance. And it appears blurred when the surface locates at different other distances like this. And as a result, projected results become like this, and only the middle image appears focused and the others appear blurred. So in our focal sweep projection system, we place a focus tunable lens, and we modulate its focal length back and forth very fast at more than or faster than 60 Hertz, so that human observers cannot perceive the modulation. Then the perceived projected pixel actually forms the same spatial intensity pattern, which is called point spread function, or PSF. And the important point is that the PSF is depth invariant in this case, at least within the range of the focal sweep. Then we can emphasize the high spatial frequency components of an input image according to the depth invariant PSF, and then project it from the focal sweep projector. Then we achieve an all-in-focus projection. So this is a prototype system. We just place this small lens in front of the projector. And as you can see, so when we modulate the lens at 60 Hertz, we cannot see the modulation. Actually, the camera cannot see the modulation. And then when I move the screen back and forth in front of the projector, the projected image is always very, very clear in a focal sweep projection, while we found it quickly get blurred in a normal projection system. So this is the quick comparison. So another common problem of projection mapping is interreflection. So in this example, an image is projected onto a corner surface or corner screen, and where the light interreflects from one side to the other side, and it undesirably decreases the contrast of the projected result. So the contrast degradation is also caused by environment light. So we solve the contrast reduction problem due to the interreflection as well as environment light by dynamically modulate the spatial reflectance pattern of a projection surface. So we apply a photochromic material that is usually used as a UV checker, and it can change the light absorption property by UV illumination. So we paint this material and use UV LED array to manipulate the reflectance pattern of the projection surface to increase the contrast of the projected result. And this is our prototype. We place the photochromic screen in front of the UV LED array, which can be actually replaced by a UV projector for more 3D shape object. And this is an example of the reflectance modulation. And we project an image onto this surface to see if the contrast is improved. And here's the result. So we projected a dog face image onto the surface, the corner surface. And when we focus on these two areas, projection mapping without reflectance modulation provided less contrast result than the target image. For example, in this eye area, the contrast becomes very less. And on the other hand, our method provided better contrast and a better image of an increased contrast. Okay, the next topic is geometric registration, which is one of the most important technical issues in projection mapping, especially in dynamic projection mapping, where target objects moving around in front of the projector. And if you project an image without considering the registration, your result would be very bad, like this in the middle. And when the projector is registered correctly, then the projected result becomes more impressive. So many of dynamic projection mapping research or systems applied visual markers or motion capture markers on the object and measured the pose and orientation of the object by them. So you can see these silver dots on the forehead are the markers. And this means that we can see the markers actually, and these markers actually significantly degrade the immersion or the illusion of projection mapping. So we developed a technology to visually diminish the markers using a projector camera feedback system, and we fabricate a projection object on which markers are printed from a full-color 3D printer and register the projector to the object. The projected images seem to be attached on the surface, but you can see the markers, which are very non-desirable. So we diminish these markers by controlling the intensity of the projected image per pixel on the per pixel basis. So specifically, we increase the light intensity on the dark surface area and decrease the light intensity on the white surface area. And this makes the markers almost invisible. But we propose another solution where we tried to optimize the projection object such that the object itself emits the invisible identification information. So to this end, we used a multi-material 3D printer and embed optical fibers in the object, which transmit blinking IR or infrared light from the bottom to the surface, like this. And we optimize the roots of the fibers so that the multiple markers emit the same blinking pattern. So here are fiber routing results and fabrications of other objects. And our objects have seven holes on the bottom where the infrared LEDs are attached. So the fabricated. So the fabricated markers work quite well in our dynamic projection mapping applications. So especially it worked even when the object moves in a significantly larger space than what the existing technologies cover. And it works in a case of a large area occlusion. Because each marker has unique IDs. So actually, we can achieve a markerless dynamic projection mapping in some cases, such as human faces, because human face capture and tracking have been already intensively researched in computer vision field, and we can use such technology to know where human facial components locate in a captured image without any markers. So once we integrate a facial capturing system, we can attach images on a face even when it is non-rigidly deformed without markers. But some of you might be afraid if it is too bright. Yes, it's bright, very bright. And so we basically fill the eye areas with black color so that bright light does not directly hit to human eyes. But yes, it is a technical limitation at the moment to be solved in future. So we tried to solve another essential problem in projection mapping, that is, if there is a mirror object, we cannot control its appearance by the projection image due to the specular reflection. So main idea to solve this problem is changing the appearance of environment, not the object itself, but we change the appearance of the environment, then to control the appearance of the glossy surface as the appearance modulation, appearance control of the environment reflected on the glossy surface. So we use a stereo projection system that provides disparity images to left and right eyes and track the viewpoint. Then we compute the environment appearance such that the mirror reflection of the environment is close to the target appearance. So this is actually mirrored surface, but we use our technique to change the appearance of that surface and this is without our system. We just project this brick image on the wall. So you can see that this is just a mirror object. And yeah, this is another example. And this is a kind of funny example of our method. So we cannot manipulate the appearance of a surface on which glossy and diffuse reflection areas are next to each other, like this. So in this case, we cannot change the appearance of this upper logo area. But if we use our technique, we can change the appearance of that area as well using I think in this application, we use a LCD monitor in front of this MacBook. And using projection mapping technology. So here we project images on this area, and on that upper logo area we use the environment appearance control. So we also tried to solve another important technical issue, which is shadow. And we got an idea of the solution from surgical lamps, which can illuminate the affected area of a patient even when the doctor's hand covers up that area. The principle is very simple. So the light comes from a large angle so that only a part of the light is blocked by the hand, while the other still illuminates the affected area. So there is no shadow. So this shows our demonstration of the technology. So as you can see, there is no hard shadow on the object even when a user covers it or touches it by their hands. So even when you cover this object, how can I say it? like this, still you can see the projected image is projected on the object. So you can compare it with a normal projection mapping in this case. I think this shadowless system provides more natural impression. And the trick behind it is this optical element, which is actually which is a micro mirror array plate, and basically used for aerial or mid-air display, but we use it for projection mapping. And this optical element actually works as a large aperture lens, and we place the mirror-shaped object in the other side of the element and project images onto that mirror-shaped dummy object. And this reflected light goes through this optical element onto the target object. And if the optical element is large enough, like this, your hand cannot block all the light from the above. It creates the shadowless effect. So we also tried to modulate haptic material sensation by the projection mapping using a cross-modal effect. And when you touch a soft object by your finger, the texture moves toward your finger, right? So we emphasize the movement of the texture by projection mapping, and we can actually make a soft object softer than the actual. And we conducted a psychophysical experiment and derived a computational model that can predict how soft the touching object is under our projection mapping. Then we can control the softness of the object without any haptic devices. We also tried to modulate the tactile shape sensation using a similar trick, and we deform the apparent shape of an object by projection mapping to tweak the shape sensation. So as you can see, we deform this object visually like this. Then the user perceives the shape of this object a little bit changed towards the visually deformed shape. Okay, this is the last slide. And I introduced, in this talk, I introduced a part of our achievements in this Shitsukan project. And we believe that to achieve real material modulation by projection mapping, we need the joint optimization of the surface, hardware, and optics with computational algorithm and deep understanding of human perception. And that's all my presentation. Thank you.
Thank you. So, any question? So you did a lot of works. So what is the next challenge? In this is just a secret.
No.
So what is the most difficult problem in the projection mapping technology?
The most difficult problem of the projection mapping is this now. So in a bright environment, the projection image gets, the contrast of the projection image becomes very low. So I want to, how can I say, use a projection mapping technology in a environment light environment. So it is. I think I want to solve this problem in future.
Especially in the daytime.
Yes, in daytime.
Okay. Any question? Please.
About shadowless projection, how do you control overall brightness? So detect occlusion and then
No,
compensate?
in this application we don't control the brightness, because I think so if you cover this object, the object becomes a little bit darker because some lights are blocked by the hand. But I think it is more natural. Because when in a normal environment, you cover some object, then the bright, how can I say, the illumination onto that object becomes a little bit reduced. So I think this can imitate or reproduce that effect.
Ambient occlusion.
Yes.
Okay.
I also have a technical question about that project. So you showed how you can illuminate the same point from different directions, so it's fine then if some of them are occluded. But in addition to the angular coverage, you also have spatial coverage because different parts of the object are illuminated with different colors. So how do you do both of that simultaneously? Do you need many mirrors, or
you mean you want to project different colors onto the same point, but from different?
No. I mean, like the bunny, for instance, that you showed. There's a checkerboard with different colors. Yeah. So there is spatial variation, but then you also have, basically you're projecting a kind of a light field because at every point there's light coming from different directions. Yeah. So I was just wondering how you do both of those things at the same time.
In this project, or
yes, in this project, because the mirror, it means you're doing something that's 4-dimensional, but the mirror is only 2-dimensional. So.
Oh. What can I say? So this mirror, this is not mirror. Sorry, this is micro mirror array. So this is a kind of glass plate, and there are a lot of small, tiny mirrors arrayed like this, and there are 2 layers. And one layer is like this, and the second layer, the mirror is arrayed vertically, perpendicularly. And this gives you, so the light reflected on this glass plate twice, then it comes back to the same, how can I say, direction, mirror direction to the other side. So this, by using this optical element, we can actually, I don't do anything about the controlling this stuff, but we just put an object here, just a mirror position, and then this optical element not automatically, but physically just collect this light ray going to this.
Okay, makes sense. Thank you.
Okay.
Okay. Any other question? Okay. Thank you.
Thank you.